Hello dear students and Assalamu alaikum. I welcome you all in the class of partial differential equations. So today the topic is regarding Fourier transform techniques for solving partial differential equations. Initially we will define the Fourier transform in that lecture, and after that I will tell you that eventually what is the definition of Fourier sine transform and Fourier cosine transform. But before going to the formal definition of Fourier transform, it is important at that point that you should learn what was the motivation behind defining the Fourier transforms for partial differential equations. Just like we have the other integral transform which we have studied in the previous semester, Laplace transform. So analogous to that we have Fourier transform and Fourier sine transform, Fourier cosine transform as well. These integral transforms are very useful to solve the partial differential equations. So the motivation behind this transformation is that if you remember from the previous class that if a function is periodic, so this is written before your screen, that suppose that if f is periodic, then it is possible to analogously define that function or observe the equivalent form into sine cosine oscillations. So the sine cosine behavior of a function which is periodic can be elaborated, and this was given by Fourier, known as Fourier series of a periodic function. This has been written in equation 1, and the coefficients analogously can be calculated as these integrals an and bn. So this has been already studied in the previous class, that if a function is periodic, we can analogously define and construct the sine cosine behavior of that function, and just like we have Taylor series or Maclaurin series of a function. So if a function is periodic, then its sine cosine series can also be written. But there is a possibility that a function is not periodic. So in that case what we will do, we will suppose that its time period is approaching to infinity. Okay, so initially that was periodic, but what I am trying to do, that suppose the given function is not periodic, so ultimately we cannot talk about the Fourier series for that function, but yet we can elaborate that idea in the proceedings, that what will happen if the function is not periodic, and what sort of changes will be there for the Fourier series of that function which is not periodic. So I am not going to elaborate all these steps, because these are very simple mathematical steps, and if you want to learn, you can discuss with me in the class. But the important aspect is that if your function is not periodic, you can have a few steps of calculation, and after that ultimately you will understand what. So when your function is periodic, when f of x is periodic, so what will happen? There is a series formation of that function which is called Fourier series. Okay, Fourier series. So this is known from the previous classes. Okay, previous knowledge, or you can say previous classes. Okay, many of you will know that if a function is periodic, you can talk about its Fourier series. But what happens if it is not periodic? So the second goal is that if suppose that on the other hand, if f of x is not periodic, okay, so what will happen? We will suppose that it is periodic. It is periodic with period approaching to infinity. Okay, so this is the change we can suppose if the function is not periodic. So what will happen, the steps between this I am not going to explain in that lecture, but yet if you want, I have uploaded the lecture with the explanation for these steps. If you want, you can understand and you learn from the video lecture which is uploaded on YouTube for the proceedings for Fourier transform definition. So these steps are eliminated when you will apply some mathematical steps and Fourier series will change to a new form. So what will be that new form? This is very important. So what I am going to do is that first of all, the function is not periodic and we will suppose that it is periodic with period approaching to infinity. So what will happen to the Fourier series? Okay, Fourier series will change to a new form and this is called Fourier transform. Okay, so if you want that what are these steps, I have uploaded already on the YouTube the video lecture number I think 10 which is related to the mathematical steps of Fourier transform, okay, and some examples as well. So so the Fourier series will become Fourier transform, and this is the definition that what do you mean by Fourier transform. Okay, so let us formally define the definition. Let f be a function from minus infinity to infinity, which means that your function is defined on the whole real line, okay, to the r. The answers or the range can be from the real numbers or can be from the complex numbers. So the Fourier transform will be what? Fourier transform will be 1 over square root 2 pi minus infinity to infinity f of x e to power minus omega x dx. So this is the actual definition. Capital F is used for Fourier transform of small f of x, okay, and the definition is what? Definition is 1 over square root 2 pi, okay, 1 over square root 2 pi, yeah, 2 pi integral, okay, integral minus infinity to infinity. Your function has to be defined on the whole real line. So if the function is defined for the whole real line, then you can talk about the Fourier transform f of x, and you should multiply this with a factor which is known as kernel of the transform. Okay, if you remember, kernel of the transform for Laplace transform was e to power minus st. Now the kernel is e to power minus iota omega x. Okay, this is the transform kernel dx. This is the actual definition, and the variable of the transform in the Laplace we used s, and in Fourier transform we will use the variable omega throughout the discussion. The notation for Fourier transform, short notation, is f cap. You should remember that. So the short notation is f cap. Okay, if you are solving a partial differential equation, you can name your Fourier transform new variable as f cap, okay, like that, f cap of omega, because the domain is now used as omega. This is a symbolic representation of Fourier transform, and this is the mathematical description that what is the Fourier transform. So this is the ultimate definition, but there are some conditions when a function. So the big question is that when the Fourier transform will exist, okay, we should do it like that, will exist. Or the second question is that for which questions, for which functions the Fourier transform actually exists. So the answer is that for the functions which are absolutely integrable, okay. So I am writing there with the correspondence that if you are having for any function the integral minus infinity to infinity on the whole real line, if they are absolutely integrable. What is the mathematical meaning of absolute integrable? The modulus of these functions, okay, in the integral form will be a finite number, okay. So if this happens, okay, This is the existence criteria or condition for a function to have Fourier transform. This is the sufficient, okay, you can say sufficient condition. If a function is absolutely integrable, Fourier transform exists. This is the main condition. There is one more condition which I am not going to tell right now, because this is the big question for all of you, that what is the condition. So this is the question. Okay, the question is that what is the main condition for a function to have Fourier transform. Okay, this is a big question. So if you don't know what is the main condition, I have told you that function has to be absolutely integrable, but there is one more class, okay, one more class of functions, for a class of functions. Okay, what do you mean by class of functions? It means that there is a group of functions which or a set of functions which satisfies one condition, so their Fourier transform must exist. So this is the main question, and you will get the answer in my lecture. If you learn, then it will be easier for you that what are the main functions for which the Fourier transform actually exists. Okay, the main idea for existence is that what the student don't understand. To exist means to be approachable, or to be if a number exists, okay, if a thing exists, it means that it is imaginable, it is approximatable. Okay, for example, pi is not an existing number, it is an approximation. Okay, so you cannot say that pi exists. Pi is a number which is not possible to be approximated. So we don't say that the pi exists. Actually, you cannot calculate what is actual value of pi. So existence means you are dead sure what is the value. So this is the question for which functions actually the Fourier transform actually exists. You will give the answer, or you will define a class for which the transform exists. And idea is that you should go for the book of Devnath, and this lecture 1, you will learn that for which functions the Fourier transform actually exists. Okay, so for the calculation point of view, if you are having a problem, so let us have an example. So f of x is equal to e to power, okay, e to power minus okay, x mod. Okay, this is a function, and domain is minus infinity to infinity. Okay, I have written a function, and the question is find the Laplace, find the Fourier transform. Okay, find the Fourier transform. So how you will find the Fourier transform? The symbolic representation you will write there. What is the symbolic representation? First of all, write the definition. Okay, so first of all you will write up the definition, and there you will put, instead of f, you will put e to power minus x mod. Okay, you will put that, and now the main focus is to solve that integral. This was I was telling in the yesterday's Zoom meeting, that you are now able to solve these kind of integrals. You know how to solve these kind of integrals. How you will solve? Okay, there is x mod. You know that x mod for negative values is different from the positive values. So the domain will be splitted in two parts. One will be integral 0 to infinity. Okay, first of all write there 0 to infinity, minus infinity to 0. Okay, minus infinity to 0, and the other thing will be plus integral again 0 to infinity. So you will be your integral will be split into two parts. One is from minus infinity to 0 and the other is 0 to infinity. So what is the integrand from minus infinity to 0? This will be similar because there is no modulus there. E to power minus x mod. X mod for negative values, because x is running from minus infinity to 0. So you know that for negative values the x mod is minus x. So what will be the answer for that? The answer for that is e to power, okay, answer for that e to power minus, what will be the answer for x mod? X mod will be minus x, because x is between negative entries, so mod has to be positive, so mod will be minus times for that values of x, because x are negative, so minus and this negative will become positive. That is why the answer for the x mod will be minus x, okay. And the second part is that e to power, this will be similar because there is no modulus there, and dx will be also similar. Similar to that, if x is between 0 to infinity, since x is already positive, x mod will be x, because if a number is 5, x mod is 5, but if a number is negative 5, like that, here we have negative entries, so the modulus will become minus times minus 5, so the answer is positive 5. So there will be the total answer for integrand. The total answer will be that. What I was trying to tell you, that the modulus answer will be e to power minus x only. So your integral actually will be split into two parts. Okay. So you will integrate. How you will integrate? Okay, I will elaborate some steps for you. This is the integration. I think you all know how to integrate, but let us just write up there the values e to power minus minus plus and e to power minus. So I am writing only one time. The answer will be no, I'm sorry. The answer will be, okay. The answer will be e to power minus iota omega x plus x, okay. This will be the one integral, and the second integral will be e to power, okay, e to power, there is dx as well, e to power, bases are same, the power will be added, so what will be the answer? E to power minus iota omega x minus x. So these are two separate integrals, and the integrand is not similar, almost they are look like exponential functions. So the main task is that you should find the integral. So how you will find the integral? Okay, sorry, you will find the integral like that. This will be equal to exponential integral will be similar, okay, similar, and actually you will apply the limits. How you will apply the limits? First of all, symbolically you should write the upper and lower limits. So what is the correct symbol there? Okay, let us make the symbol. Yes. Okay, I can do one more thing, that instead of making a symbol, you should write that in that form. Yeah, this will be good for you. Yes, in that form, and there you should write upper and lower limits. The lower limit is minus infinity, okay, minus infinity is not a good option to write, not a good representation to write infinity, because infinity is not a number. Instead of minus infinity in the calculus, we should do put a value and there will be 0, okay. I will tell you what is a, okay, plus the second is again, okay, you have to divide as well, okay, you have to divide as well, the divide by the derivative of the power. So derivative of the power is minus iota omega plus 1. Okay, so this is the one term. Second term is that similar to that, but there will be some changing, because in the exponent we have minus x, okay, and in the denominator the derivative will be minus as well, so it will become minus iota omega minus 1. This is the total answer, and for the whole thing, just write one more step, that limit is there, and the limit a tends to, not x, a tends to infinity. Because in calculus it is not a good way to write there minus infinity. Minus infinity is not a number. Minus infinity is a limit for which a function can approach. So it is good way to write there a approaches to infinity and a is a number. Okay. Now what is the next step? In the next step you will do apply the limits. So how you will apply the limits? Upper limit will be 0, e to power 0 1. Okay. So I should write first of all the square bracket. Yeah, there is a limit. Okay, there is a limit, and there is also e to power 0 1. Because upper limit is 0, so there will be 1, and the lower limit is that e to power minus, okay, e to power minus iota omega a plus a. This is the total answer. Okay, and it is better that you should write the denominator as well. So in the denominator you have minus iota omega plus 1. This is your denominator. Okay, you have applied the limits, and the denominator is similar. Plus the second thing, I think this will be similar to the first term, because the only difference is with the exponents. So you will apply the upper, sorry, there was not upper limit was, so lower limit was 0 and upper limit was a. This was the mistake. Okay, minus a to 0 and 0 to a, and a is approaching to infinity. Now you will apply the upper limit. So upper limit is e to power minus iota. So this will be not there, because upper limit is a. So e to power minus iota omega a plus a. Okay, sorry, not plus a, minus a, because the exponent is for minus. And lower limit become makes the integral 1. Okay, and in the denominator you have e to minus iota omega minus 1. So this is the total answer for applying the upper and lower limits. Now you have to solve these this ratio and apply the limit. So what you will do, actually the integral will be equal to Fourier transform will be equal to you have to calculate the limit actually. So when a approaches to infinity, okay, or you can do one more thing, that yeah, if a approaches to infinity, then what will happen to that term? Okay, or what will happen to that term? So when a approaches to infinity, this term will approach to 0, because a is approaching to infinity. So 1 over infinity, the answer will be 0. Okay, and one more thing you can do there, you can actually split this. So because limit is applying here, we should focus on that term. Okay, what will be that term? That term will give you e to power a over e to power iota omega a. Okay, so but if you apply the L'Hopital rule, the focus will be not there, and there the limit is actually 0, because something power minus infinity approaches to 0. So the main focus is there. Okay, so take that outside and just focus what will be the limit, because there is no a other than this place. Okay, what will be that limit? So that limit will be e to power okay, I should write there e to power minus iota omega a, okay, okay, you can do one more thing, control C and denominator. So in the denominator this is e to power plus iota omega a, and in the numerator you have e to power omega a, okay. So you don't know what is the answer for that limit, but let me remind you that when you have limit a approaches to infinity, e to power a will approach to infinity, e to power iota omega a will also approach to infinity. You can take real and imaginary parts outside, so the ultimate answer what I feel will have to be 1, because numerator and denominator both are approaching to 1. So you will apply the limits, okay, and the ultimate answer for that will be 1 over okay, not 1, if you put the limit e to power minus, okay, e to power minus so what I was trying to tell you, that ultimate answer for that limit will be what? The ultimate answer for that limit has to be 0, because in the numerator you have a smaller factor than the denominator. In the denominator the factor is bigger, and the ultimate answer for that limit will be 0. Or you can apply any other law from the basic classes, you will see that the limit answer is 0. This is your exercise, okay. So to prove that the limit answer for that ratio is 0, and the limit for that will be what? The whole quantity is negative, okay, e to power minus iota a omega minus a. So ultimately the answer will be 0 for that as well. Eventually you will be left with what? Eventually you will be left with after applying the limit. So after applying the limit you will be left with the quantity, not limit because limit has gone, and this quantity was become 0, and this quantity was also become 0. There is minus 1. You can shift minus outside, because in the denominator this will become positive. So in the numerator there will be no minus, because minus has been taken care by the denominator. This will be the total answer. And also I think we forget, there was a factor of 1 over square root 2 pi as well everywhere. So you should put everywhere 1 over square root 2 pi, okay. There is 1 over square root 2 pi, there is 1 over square root 2 pi, and there is also 1 over square root 2 pi, okay. Now you have to solve this ratio, and ultimately you will see that after the LCM, what will be the answer? So after the LCM, this ratio will become because in the denominator is a minus b and a plus b product, so it will become a square minus b square, but minus is with the iota omega, so it will become 1 square will be 1 plus iota minus iota omega square, it will become omega square, okay. And in the numerator we have, for that factor we have 1 plus iota omega, and for that we have 1 minus iota omega. So ultimately we have 2, 1 plus 1 2. So the answer will be square root 2 over pi, okay, square root 2 over pi, okay. And the other thing is that 2 over 2 is not there, 1 over, okay, ratio 1 over 1 plus omega square. This is the total answer for your functions Fourier transform. So this is the method that you should understand how to apply Fourier transform. More than this, I have also said to you that please understand the definition, and there is inverse Fourier transform as well. So what is the inverse Fourier transform? there is no difference. You will apply the similar definition 1 over square 2 pi minus infinity to infinity, but there will be Fourier transformed function and e to power iota omega x d omega. So this will be the total answer for your inverse Fourier transform. Number 1. Number 2 is that just like that, find the Fourier transform of the function. This is the example, if you understand. Is a piecewise function, and when you apply the definition, you will understand by very basic steps that actually the answer for the Fourier transform is 1 over square 2 pi 2 sine xi l over xi. You can use xi parameter, omega parameter, it's not a problem. And there is a properties there are properties as well for Fourier transform. This is your exercise to just understand what is the Fourier transform of the derivative, what is the Fourier transform of single derivative, that's it. And you have practice problems as well, so please try to understand that what are these practice problems. This is the first main thing. Second is that just like in the previous classes, we have Fourier transform, Fourier series definition, right? You have Fourier series. Similar to that, you have Fourier sine series and Fourier cosine series as well. So analogously, we have Fourier sine transform and Fourier cosine transform, because look, in the Fourier transform you have the definition e to power minus iota omega x. So by Euler's formula, you know that this is equal to cos of iota omega x minus sine of iota omega x. Okay, this is, you know, by the classical complex analysis. The real part will become Fourier cosine transform, and the imaginary part will give you the Fourier sine transform, but not between minus infinity to infinity we will discuss, because we will take only the even part for that transformation. Again, I am not going into the discussion of even part, but rather you should understand what is the definition. The Fourier cosine transform of a function is given by that integral transform, 0 to infinity square root 2 over pi f of x cos omega x, and inverse Fourier transform is given as the similar thing. So Fourier sine transform is given, just the one difference, instead of cosine we have sine, and the same inverse is similar to that. Again, I am stressing, I have written there what is the Fourier sine transform of the derivative, what is the Fourier cosine transform of the derivative. Look, there is the formulas. These formulas you should just read out, because in the next video lectures I will tell you how to implement them into the original partial differential equation and solve the corresponding partial differential equation. So just like I have told you how you can find the Fourier transform, similar to that, these are the questions. So this is the question, you should calculate Fourier sine transform and Fourier cosine transform for this one question. And in the Debnath book, if you go there, there are also Fourier transforms, Fourier sine transform and Fourier cosine transform. Look, there is the main definitions. So there also are many examples you can go and practice before going to the original equations, original questions in the exercise. So this is for today, that you should go, and Fourier sine cosine transform definitions are there. I have thoroughly told you about the definition for Fourier transform, and eventually you will understand. So what I was telling to you, that you should, this is the Fourier transform, and Fourier sine cosine transform you should understand and study the definitions. And there are questions in the book and in the bottom of the lecture slides as well. There is only one question, but again the golden question is that you should give me two examples, okay, two examples for which Fourier transform does not exist. Okay, does not exist. Examples of any two functions, examples for any okay two functions for which Fourier transform does not exist. You should give me, and this is a good exercise actually, so such that you will understand what is actually Fourier transform. So this is the definition. The hint is that what are the functions for which this integral does not exist. If the integral does not exist, so it means Fourier transform does not exist. So you have to classify these kind of functions. Okay, this is the main question, and I hope you will understand and give me the answer. And in the next lecture I will tell you how to apply Fourier transform, Fourier sine transform and Fourier cosine transform to the partial differential equations, and how to solve the transformed equation and then apply inverse Fourier transform, inverse Fourier sine or inverse Fourier cosine transform. This is the next lecture, and thank you very much for listening. Please subscribe the channel. If you like the videos, please share as well. Thank you very much.